Oh, guys, we're talking about soil. We're talking about dirt. The most important part of our ecosystem is this gorgeous bit of dirt that we have. All of this soil with all the nutrients and the water, all of it. We would not have life. We would not have humans, would not have primary consumers unless our plants had something to get their nutrients in. So thank you for mud. Thank you for soil. We are lucky to have it. Before we move on, this is one of my favorite books. This is called There's a Hair in My Dirt, and just a fantastic representation of why soil is so important and where it all comes from. So I'll probably read that to you guys later. All right, let's talk about why soil is so great for us. It does numerous things and provides lots of ecosystem services. First, stores a huge amount of water. That is massive. It is cleaning and purifying our water, so as the water infiltrates through it, it is being cleaned, it is being purified, nutrients are being pulled from it. Very important. It cycles our nutrients, nitrogen, phosphorus, and it's necessary for root growth of most of our terrestrial plants. And like I said, if there's no terrestrial plants, then there's no primary consumers, and if there's no primary consumers, there are no humans. As mentioned, soil is going to serve as this water reservoir, providing plants with so much access to water. Most importantly, it's after the precipitation happens. There are minerals inside our soil that will actually attract water molecules. And so because of that, the water is going to store and hold out in our soil. If we didn't have this, then our plants could only grow, could only photosynthesize when it was raining. And then after that, they wouldn't be able to. Fun fact, more of the Earth's water is in soil than in our freshwater rivers. Fascinating. Very important, clearly. As I also mentioned, it is a structure for our roots. All of our vascular plants, which are our producers, and they form the base of our food web, they are these plants that need the soil in order for their roots to extract everything they need. So for photosynthesis, we need oxygen, we need water, and for later on, for assimilation, we're going to need nitrate, we're going to need phosphate. All of those things come from this soil, most importantly. And in addition, we need structure. We need something to hold our plants up. And that's what the roots do, but they need soil in order to do that. Healthy soils are going to be filled with these living organisms, our arthropods, our worms. They're breaking down all these nutrients. They're a decomposer. They're bringing these nutrients back into this soil here. And then our bacteria, which we know they are cycling those nutrients. They're cycling our nitrogen. They're bringing it from the atmosphere. So all this living stuff is so important for our soil. And then also our soils contain an enormous amount of decaying plant matter. This is good. Fun fact, the reason why fall has that smell is all because of this decaying plant matter that's happening. So therefore, our plants are our second largest carbon sink on the planet because all this biomatter has fallen. All of it full of carbon is all fallen all around here, and it's just hanging out right there until it is decomposed. We'll talk about this in our other video, but our soil is porous. That's extremely important. And these pores, they fill with water and air. And all of these molecules here, they're going to attract water around it. So that's how it's able to hold that water for longer periods of time. The roots are then going to move into these pores to get the water that they need. And they're also going to breathe because we also have oxygen flowing through these pores as well. As you'll learn about in the other video, clay is a massive component of soil. And clay is extremely important because it's going to actually pull positive ions from the water. It's a great source of filtrating the water for us. So those of you in chemistry remember, so clay has all these negative charges on the outside of it. It's this net negative particle, which means that all of the impurities in water are going to stick to it. So anything that has a positive charge is going to move over to it. So sodium used to be out here, now shoop, it's over here. Calcium used to be out here, now shoop, it's lining up with the clay. So it cleans our water, which is very important. And it was going to pull all of these ions from the water. So an important thing to have in our soil. This is the same thing I just repeated, so we'll skip that slide. Okay, super important slide here. These are all the factors in how soil is formed, and they affect the soil that we're going to get at the end of the day. The first most important part is the type of parent material. Is this igneous rock? Is this granite rock? Is it limestone? Whatever it is, that is going to be the base that is broken down by wind and rain, and it's going to keep that basic chemistry of those rocks as we break it down to smaller pieces. The second is the climate, the average temperature, the moisture. That all has an impact on the weathering and the leaching. Leaching is an important word. Leaching is when nutrients that are in the rocks are kind of pulled out. They're brought out and they're entered into the water. And they're going to be redistributed all throughout the soil from there. Topography is a big deal. This is the slope of the land. And as you guys know, the steeper the slope, we're going to have more erosion. The flatter the slope, we're going to have less erosion. All biological factors, so these could be any plants, animals, microorganisms, anything that's in that soil, kind of turning it up and allowing the nutrients and our carbon, nitrogen, phosphorus to flow. And then finally, time. Soil formation is continuous. It's always going on. There is no end to this. It actually needs to be considered a non-renewable source because we will run out of it. It takes generations, it takes centuries for this soil to turn over and be full of nutrients again. So it's very important, and this formation's constantly going on. All right, let's look at this whole process here. This process is taking us from the parent material, just the rock, until we have gotten to soil at the end. Now, we have talked about primary succession. This is very similar to that. You know it's going to take hundreds to thousands of years, but it is the process when we take this parent rock, it's going to be broken down into smaller pieces through mechanical processes, through chemical processes, through the crust, turning and tearing it apart, and then also through chemical weathering that's going to break it apart. And then, as you know, we're going to start to get a few bits of organic matter, and that organic matter is going to start to break it down and going to be that first bit of biomass when it dies that then allows for more plants to come in. And those roots are going to start breaking down the soil, creating more soil, and so on. So we're starting with our parent material. We're going to end up with a bunch of soil and then our bedrock underneath. All because of processes that are breaking our minerals apart and then changing our minerals into new components that are used for our soil. Okay, let's talk about these mechanical processes just real fast and what they're doing. They are turning this parent rock into soil. It happens through a few ways. First, temperature changes. Heat causes expansion, and then cold causes contraction, and over time, that is going to break our rocks apart. Ice wedging, I'm sure you've seen this before. When ice forms, it expands. So if I put a glass container of water in the freezer, it's going to shatter the glass because it's going to push the rock apart. Water is going to come in here, it's going to freeze, and when it freezes, it's going to push our rocks apart from each other. Root growth, same thing. They're going to dig in here and break these rocks. I'm sure you've seen sidewalks where roots have pushed concrete around. And then finally, abrasion. This could be water, this could be wind, this could be glaciers, or this could just be crust movement that is causing these rocks to slide past each other and fall apart. So through these mechanical processes, we're going to take our parent rock and we're going to break it down. We could break down into gravel. Gravel is about 2 millimeters. It could break down into sand, which is much smaller. And then even further, it's going to break down into silt. And then finally, actually you would not be able to see it on this scale, is clay. It's going to break it down and through some more chemical processes into clay. On the other hand, our chemical weathering is going to happen when rainwater penetrates through it. So fun fact, rainwater is actually acidic because we have a lot of CO2 in the air. When water mixes with it, we're going to get something called carbonic acid, which is H2CO3. That carbonic acid is then going to penetrate through the rock here, and it's going to dissolve some of the minerals, causing these chemical reactions that are turning these minerals into other things like clay. When this chemical weathering happens, we get clay from it, which is an important part of our soil. And then as you remember, this whole process is slow. Just like primary succession, it's going to take thousands of years to go from soil to trees. So as I mentioned, I think in another video, we need to remind ourselves that this actually is a non-renewable resource. As humans, we could run out of fertile soil in our lifetime, and we're not going to have the time needed to turn it back into fertile again. We cannot make more soil, unfortunately. Okay, here we go. This is important stuff. This is what you need to know for AP are the soil horizons. These are the layers, the different layers of soil as we go deeper into the ground, going from the surface down to our bedrock. Each of these layers are a soil horizon, but the whole thing, is a soil profile. And this shows us the composition and the thickness in different locations. Okay, so normally we have 4 distinct soil horizons, A, E, B, and C, with organic material at the top and then bedrock at the bottom. So we need to know the layer and how they go from top to bottom. So on top, we have our humus or organic material, that is horizon O. Then we have horizon A, which is topsoil. Then we have horizon E, which is the alluviated horizon. Then horizon B, our subsoil. Then horizon C, our parent material. And then our bedrock. So many different ways for you to remember this. I like to think that we go A, B, C with an O on top, an R on the bottom, and an E in between. That works so much better for me to go A, B, C, O, R with an E in between. However, you could also say that Oreos are everything because cookies remain That's one I've seen. Or I've seen only apes eat bananas completely ripe. You know, so many different ways to remember this. I'll let you figure out what you want to do. All right, we're going to start with O. O is not really soil. It is just this layer of organic material formed by the decomposition of leaves, of some biotic matter, and all of this material is going to come together to form a very organic layer on the top called humus. It is not hummus, it is humus. And most important, it is full of nutrients. So many nutrients because it's got all this nitrogen compounds in there, tons of carbon, tons of phosphorus. Not really soil, but so nutrient rich. Very important. Then we have our A horizon. This is our first layer of soil. We call this one the topsoil because it's on the top. And it has this broken down mineral content from the parent rock, but it also has the humus from the layer above it. So important. It is home to so many organisms. And because of that, it's very porous because there's all these little creatures making these pores and these burrows. So it's very alive and full of these air pockets, and therefore also full of nutrients to provide our plants above it. All right, then we have our E horizon. This is the alluviated. That means that water has come through it. And this water has come in, drained, and gone down, and it has leached the clay. It has taken the minerals, it has taken the organic matter. There's not much left behind besides sand. It has a lot of sand and a lot of silt in it. But all the nutrients are gone. All that organic matter is gone. And all the minerals are gone. So that's why it's very light colored like this, because there's really not much left. We don't always see it, but when we do, it's normally in older soils where over many, many, many years, water has come through and leached all of the organic matter and all the minerals from it. All right, now we're in our B horizon here. Our B horizon is called the subsoil. All the minerals that left our E horizon are all now in this B horizon. Most of all, iron. Iron, that's very important. Iron, aluminum, we have clay, organic matter. All of that has been leached comes down and is hanging out in our B horizon. And so therefore it is red due to this iron that is left over. All right, and then we have our C horizon down here. This is also called the substrata as well, another way to call it, and it is the transition zone between our bedrock and our soil. So down below it, here, we have, this is our bedrock, just plain hard rock. And then above it, here, we have soil. So it is kind of that in-between mixture of the two. Lots of parent material down here, and it is going to affect the soil above it because all this soil here came from our C horizon. And so the different biomes are going to create different soil profiles. Let's look at some examples here. Tundra, as you would assume, it is a very thin soil, low in nutrients, acidic. If you remember, it's acidic because of the pine needles, which are very acidic when they drop. And because of this permafrost, it is frozen. At least the topsoil is frozen for much of the year, so there's not a lot of biological activity happening in that topsoil. Taiga is also low in nutrients and primarily because of the super high acidity, We have so many pine trees in the taiga, and those pine trees are going to drop their needles, causing a very acidic nature, and very few things can live in that, so therefore it's low in nutrients. Temperate seasonal forest. This is what we have here. Thick, beautiful topsoil. We have some nutrient levels. They're not too bad. And this is all because of the leaves that are falling. So when the leaves fall down, they're going to be decomposed, producing a beautiful nutrient. Our best, however, is the temperate grasslands. Deep topsoil, very rich in nutrients. This is the best soil that we have. Then we have the tropical savanna. If you remember, savanna is much hotter. And because it's much hotter, it's drier topsoil. Less water, it's very thin, and it's unfortunately very low in nutrients because the water leaves and the water takes the nutrients with it. Desert, as you would assume, very dry, very thin, very sandy, and sand can't hold on to water, so therefore the nutrients go away with the water. Tropical rainforest, you would assume that this is a very good topsoil, but it is not. And that's because we have so much rain here. And the rain is going to take away all the nutrients. They're all going to leave with that rainfall. And in addition, any nutrients, any biomass we do have on the ground with a tropical rainforest, it's going to be consumed right away by our biotic creatures down there. And then finally, we have our temperate rainforest. Great thick topsoil, high in nutrients, because we have all these leaves that are dropping, but you do not have all of this biotic interference that is consuming the biomass. Oh, that was a lot. You guys are doing great. We're going to play with the soil, and I'm so excited. Have a lovely day.